and he will talk about homogenization of optimal control problems in the setup of oscillating boundary domains. And he is still in PhD. He's almost finishing. As he was saying, he about to finish his PhD in a couple of months. Yeah, Apu, so it's your turn. Please go ahead.
Yeah, thank you, Ravi. Okay, so hello everyone. So today I'll be talking about, like, my talk will be divided in two parts. So in the first part, I am planning to do some homogenization of a variational problem where the coefficient of the variational problem has strong contrasting diffusivity term. And in the second part, we'll do a homogenization problem of an optimal control problem associated to the variational form. Okay. So the partial differential equation with strong contrasting diffusivity appears in several physical models, such as like modeling in double porosity model, or if effective like computing effective properties of a material which has soft core and hard core, and like material which has very high conductivity and low conductivity material, and like we try to compute like effective conductivity of a material which is made of different type of material, like one has very high conductivity, one has very low conductivity. Like, so more precisely, suppose you have a composite like this. So you have a periodic composite material which is made of this kind of reference cell. So you have like a red one which has, for example, suppose we try to compute the conductivity, or like if a or elasticity or something like that. So for time being, suppose we try to compute the conductivity. So you have a like red material which has very high conductivity. Now we have inclusion which is yellow one, which has a very low conductivity, that is like order of alpha epsilon, where alpha epsilon tends to 0. With this reference cell, we made a composite material like this. Now we try to analyze, like we try to do multi-scale analysis on this kind of composite. When you do, for example, suppose we want to study like a steady state heat equation. So if you study on this kind of domain, in this kind of materials, the coefficient matrix A epsilon going to depend on where you are looking at. Like coefficients will be like order of 1 on the red part and order of sort of alpha epsilon on yellow part. So there is a very drastic difference between the coefficient, like one is order of 1, one is order of sort of epsilon. So in this kind of domain, when you study multi-scale analysis, so this kind of contrasting diffusivity PD will appear. So there are several mathematicians which who studies multi-scale analysis on this kind of domain. Some of them are Panashenko, Bakalov, Kursarev, Sharev, Alisili, Bushite, and so on. So these are some of them. There are other mathematicians also. Recently, in 2016, Professor Ekananda Kumar and Alisili have studied a controllability problem. Someone asking something?
No.
Yeah. So recently, Professor Ekananda Kumaran and Alisili studied a controllability problem of a wave equation in this kind of composite material. Later, in 2015, Professor Anthony Guardiolo and Alisili had studied a variational problem on this kind of domain, but this is a different setup, like in pillar type oscillating domain. So what they have considered, so to be more precise, they have considered a oscillating domain like this, where the reference cell of the oscillating pillar is given by this. So what it has, the reference pillar has a core part which is very high conductive and which is covered by a sort of insulating type material. So what they have done, they just put, like, for each epsilon state, they scale down in the horizontal direction and put it periodically over this this bottom part. So on this domain, they have considered a second order variational problem, and they have studied is a homogenization problem. So in the present, what we have done in the present article, like in my present work, we have considered a two-dimension. So it is whatever we have done, it can be generalized in any dimension. So for time being, I am just restricting myself in 2 dimension. So what we have done, so here we have considered a like pillar type oscillating domain. In the present work, we are allowing the reference cell can be any sort of shape as long as it satisfies some certain condition in x1 direction. Okay, so just to be more precise, so we have considered like this kind of reference cell. So this is just like typical depiction of our reference cell. So just for simple presentation, I took this kind of domain, this kind of reference cell. It can be any like very rough domain or sort of, but just for to see more clearly, I consider this reference cell. So what we have? So we have reference cell lambda, and I divide this lambda into two parts. This left part I denote it by lambda, that is I. I is for like insulating part, and C is denoting like conductive part. So insulation means like its conductivity is very low, and C, that is conductivity, is like order of 1. Okay. And what we do, we just like for each epsilon stage, we scale down it by epsilon, like epsilon in x1 direction, and we put it periodically over the bottom domain omega minus. So this is the oscillating domain. So this blue part is basically your insulating part, like a sort of insulating region, like conductivity is very low, that I am denoting by I epsilon, and the white part is the conductive region that I denoted by C epsilon. So on this reference cell, I need to put some assumption to do our analysis. So what we have done? So just to put mathematically all the assumptions. So I took the reference cell lambda, which is a subset of 0, 1 cross 0, 1. Again, this you can take any, it can take like 0, 1, 0 L cross 0 K, where K and L any number greater than 0. But just for simplicity purpose, I'm just taking for time being 0, 1 cross 0, 1. And this C and I are the disjoint union of lambda. So lambda bar is basically your C bar union I bar, and C bar intersection I bar, C intersection I is phi, that is empty set. And it satisfies certain properties, that is lambda Ci are Lipschitz domain. The one-dimensional Lebesgue measure of C intersection with the top part, that is 0, like bottom part, that is 0, 1 cross 0, and top part 0, 1 cross 1 has strictly positive measures. So basically that will ensure when epsilon tends to 0, this C and I both together will cover the full domain 0, 1 cross 0, 1. And for each x2, so just for to see in the reference cell. So for each x2, I'm denoting yx2 to be the projection of the line, this line over x1 axis. And for insulating part, the projection I'm denoting by yi, and for conductive part, I'm denoting the projection ycx2. So mathematically, we can write this yi and c in this way. So for each x2 belongs to 0, 1, yx2 is a collection of all y1 belongs to 0, 1, such that y1 comma x2 belongs to lambda, and ycx2 is collection of all y1 belongs to 0, 1, such that y1 comma x2 belongs to c, and for all, and for yix2 it is similar, like y1 comma x2 belongs to I. And we will also assume that for each x2, yx2, ycx2, and yix2 has one-dimensional Lebesgue measure positive, that is this one. There exists a delta greater than 0, such that these things happen. I mean, it should be always positive. Now we'll define our oscillating domain. So for each epsilon is equal to 1 by m, where m belongs to z plus. Again, one can take any sequence epsilon tends to 0. So just for simplicity purpose, we are taking epsilon is equal to 1 by m type. So what you do, we denote the C epsilon is union of all conductive part for at epsilon each epsilon level. That is C epsilon is equal to collection of like k going from 0 to m minus 1, such that x1 belongs to k epsilon plus epsilon ycx2, and x2 lies between 0 to 1. Similarly, we have I epsilon. For that, x1 should belongs to k epsilon plus epsilon yix2, and their union is denoted by omega epsilon plus, that is basically our oscillating part of the domain. So omega epsilon plus is nothing but your I epsilon union C epsilon closer, and then take interior. Omega minus is the bottom part, that is omega minus, that is the fixed domain. Here there is no oscillation. So omega minus is 0, 1 cross 0 minus 1. And the oscillating domain is oscillating domain is union of your oscillating part and fixed part. That is omega epsilon is equal to omega epsilon plus union omega minus, take the closer and then interior. Because of our assumption that we took C has sort of non-zero measure intersection with the top part, that is 0, 1 cross 1. This, when epsilon tends to 0, this C epsilon and I epsilon together will cover the full domain omega plus, that is omega 0, 1 cross 0, 1. And then the limit domain will become omega is equal to omega plus union omega minus, take closer and then take interior. Interface between omega plus and omega minus I'm denoting by gamma, where gamma is given by collection of all x1, 0 such that x1 belongs to 0, 1. Now, in order to do analysis in this kind of domain, we're going to use the unfolding operator. So just to define the unfolding operator, we have to fix some notations. So for each epsilon greater than 0, the unfolded domain corresponding to omega epsilon plus is given by omega u, that is collection of all x1, x2 belongs to y1, such that x1, x2 belongs to omega plus and y1 belongs to yx2. Similarly, omega cu, that unfolded domain corresponding to c epsilon, that is the conductive region. So that is given by collection of all x1, x2, y1, such that x1, x2 belongs to omega plus as it is, but y1 will belongs to ycx2. Similarly, we have omega iu, for that y1 belongs to yix2. Okay, and the lower and the bottom boundary of omega cu I'm denoting it by gamma cu. So gamma cu nothing but your x1 0 y1, such that x1 0 y1 belongs to boundary of omega cu. So this is nothing but the lower boundary of omega cu. Now we just will give the definition of unfolding operator. So this unfolding operator is nothing but like a map which maps a function from omega epsilon plus to r to a function going from omega u to r. So basically it takes a function from oscillating domain to a function in the fixed domain, and which is defined as t epsilon u x1 x2 y1 is equal to u of epsilon x1 by epsilon integer part plus epsilon y1 comma x2, and this epsilon x1 by epsilon integer part plus epsilon y1 always belongs to your oscillating domain omega epsilon plus. Now in our analysis we're going to use 2-3 important properties of this unfolding operator. So just we recall those. So first of all, sometimes we just restrict our unfolding operator on the conductive part, and that unfolding operator, the restriction of unfolding operator on that region, conductive region, sometimes I will denote it by T epsilon C. Yeah. So some of the important properties of this unfolding operator is given as, so for each epsilon greater than 0, this unfolding operator satisfies LP integral inequality. So it is strictly infinity, less than infinity. So this is like a LP integral equality. There is T epsilon u LP omega u is equal to norm of u LP omega epsilon plus. For u belongs to H1 C epsilon, H1 is that usual Sobolev space. So for u belongs to H1 C epsilon, T epsilon C and del x2 of T epsilon Cu belongs to L2 omega Cu. Moreover, because we have oscillation in x1 direction, the x2 directional derivative we can interchange between the unfolding operator and the derivative. That is del x2 T epsilon Cu is equal to T epsilon C del u del x2. But we cannot interchange between x1 and y1. For that we have to give one epsilon factor. So that is del y1 T epsilon Cu is equal to epsilon times T epsilon C del u del x1. And for any phi defined on omega epsilon plus or a subset of omega epsilon plus, phi tilde is always denote the extension of phi by 0 to the domain omega plus. And for every epsilon greater than 0, suppose E epsilon is a sequence in L2 omega epsilon plus, such that T epsilon u weakly converges to u in L2 omega u. Then U epsilon tilde will weakly converges its average with respect to y1. That is U epsilon tilde weakly converges to yx2, u x1, x2, y1, dy1 weakly in L2 omega plus. So basically this weak convergence sort of relate the, like, using this convergence we will come back from unfolded space to our macro space omega plus at the end. Yeah. So now let's take the first, like this is the first we'll see the homogenization of this following variational problem. So why, first of all, why you call this is a high contrasting diffusivity problem? So you see, like in our omega epsilon domain, we have chi omega minus, that is fixed part, chi c epsilon, that is conductive part, chi I epsilon, where I epsilon is sort of denoting the insulating part. So this chi c epsilon has coefficient 1, that's sort of like conductivity as order of 1, but chi I epsilon, that is insulating part, it has coefficient epsilon square. So this is like very sort of very low conductive part. So that's because of this drastic difference between the coefficient of C epsilon and I epsilon, we call it like high contrasting diffusivity problem. So first we will homogenize this variation problem in this general oscillating domain, and then we'll see a homogenization of associated optimal control problems. And in control problems, we'll put separately control on I epsilon and C epsilon. So the variational problem is find U epsilon belongs to H1 omega epsilon such that integral over omega epsilon chi omega minus plus chi C epsilon. Yeah, this chi means the characteristic function of C epsilon. So chi always, so whenever whenever I use chi, that means it is a characteristic function. So chi omega minus plus chi C epsilon plus epsilon square chi epsilon grad U epsilon grad phi plus integral over omega epsilon U epsilon phi is omega epsilon f phi. So this is standard second order elliptic variational form. And this should be holds for all 5 belongs to H1 omega epsilon, and where f belongs to L2 omega. So throughout I will be taking f belongs to L2 omega. So the Lax-Milligrom lever will guarantee the existence and uniqueness of E epsilon. So for every epsilon, we have existence of E epsilon, of such E epsilon. So what is our aim? So our aim is to analyze the asymptotic behavior of this variational form when epsilon tends to 0. So what we'll do, we'll just now I will state the limit problem, and I will show that this problem will converges to that limit problem. So before stating the limit problem, I should have to fix some limit function space where our limit homogenized solution will belong. Yeah. So for any function phi defined on omega, sometimes we may write as phi is equal to phi plus chi omega plus phi minus chi omega minus, or as a pair phi plus comma phi minus. Okay. So the limit function space h omega is the collection of all phi such that phi plus belongs to L201 colon H101, and phi minus belongs to H1 omega minus, and phi plus and phi minus agree on the interface gamma. And the norm is given by norm of phi h omega as norm phi minus H1 omega plus norm phi plus L2 omega plus del phi del x2 L2 omega norm. Now, for our analysis, we need some cross-sectional cell problem. So for each x2, we'll denote a function space corresponding to yx2. So that I'm denoting by vx2. So vx2 is given as collection of all y belongs to h1 yx2, such that so this yx2 is a one-dimensional set. So h1 yx2 such that w is 0 1 ycx2, that is projection corresponding to conductive part, it is 0. So it is supported only on the corresponding to the projection with respect to insulating part, that is yix2. So the norm on vx2 is given by norm w vx2 is norm of w L2 yx2 plus del w del y1 norm L2 yx2. And similarly, we define another space, function space, that is v omega. So v omega is the collection of all psi, which such that psi belongs to L2 omega u. Psi is equal to 0 on unfolded domain corresponding to conductive part, but del psi del y1 belongs to L2 omega iu. So basically, the function space on the function belongs to v omega is supported on unfolded domain corresponding to our insulating part, that is I epsilon. And the norm on v omega is given by norm psi v omega is equal to norm psi L2 omega plus norm del psi del y1 L2 omega u. Now we are in a setup to state our limit variational form. So the limit variational form is given as find u is equal to u plus comma u minus belongs to h omega such that ycx2 such that this ycx2 is the measure of ycx2. So integral over omega plus ycx2 del u plus del x2 del phi del x2 plus integral omega plus alpha x u plus phi plus integral over omega minus u minus phi plus integral over omega minus grad u minus grad phi plus this is equal to integral omega plus alpha x f phi plus integral omega minus f phi. Now this alpha x sort of capture the contribution corresponding to the insulating part. So what is alpha x? So alpha x given by this one. So that is measure of yx2 minus integral of yi xi dy. So where xi satisfy the cross-sectional cell problem. That is xi x2 belongs to vx2 such that integral over yx2 del xi del y1 del w del y1 plus yx2 xi x2 y1 w y1 is equal to integral over yx2 w y1. So this is true for all w belongs to vx2, and this cell problem has a unique solution again by Lax milligram. So now what we will show that our limit problem satisfy this variational problem. Yeah. So this whole thing is sum up in this following theorem. It is for every epsilon greater than 0, let E epsilon be the unique solution to the considered variational problem, and let h omega be vx2 defined as earlier, and let u is equal to u plus comma u minus belongs to h omega satisfy the limit variational problem, then following convergence hold. That is u epsilon minus converges to u minus weakly in h1 omega minus u epsilon tilde weakly converges to measure of yx2 u plus integral over yix2 f minus u plus xi x2 y1 dy1, and chi c epsilon del u epsilon plus del x1 tilde weakly converges to 0. So this all this weakly will be nil 2, and chi c epsilon plus del u epsilon plus del x2 weakly converges to ycx2 del u plus del x2, and epsilon times chi I epsilon plus del u epsilon plus del x1 weakly converges to f minus u plus yix2 del xi del y1 dy1 plus epsilon chi epsilon plus del u epsilon plus del x2 weakly converges to 0. So this so yeah, so we'll just briefly see the sketch of the proof for this theorem. First of all, to get uniform bound, so not exactly uniform, just to take some bound, first we take phi is equal to u epsilon as a test function in the epsilon stage variational form. If we put phi is equal to u epsilon, we will get this equality. Now in this equality, we have h1 bound on c epsilon and L2 bound on e epsilon, but we don't have h1 bound on I epsilon. So to observe that grad u epsilon L2 c epsilon is uniformly bounded, but grad u epsilon is bounded like sort of like order of 1 by epsilon. So we don't have uniform bound of h1 norm of e epsilon. So that makes like analysis is more delicate. So basically what we'll do, we'll try to use as much as possible wherever we have bound. Okay, and we try to capture from that the contribution from the insulating part. So now here we use we have this LP integral equality and the weak compactness of h1 omega L2 omega function L2 space. So using these things, we're going to have this kind of convergence. So because of this bound 2, we're going to have like, and the weak compactness of h1 omega L2 omega u, we're going to have there is a u minus belongs to h1 omega minus u naught, because first of all we have uniform bound in lower part. So that's why we're going to have weak convergence in h1 space in the lower part. So there are going to be a u minus u naught belongs to L2 omega u, neta which is a vector neta 1 comma neta 2, and a z which is again a vector z1 comma z2 belongs to L2 omega u square, such that u epsilon minus weakly converges to u minus in h1 omega minus, t epsilon u epsilon plus weakly converges to u naught xy1 in L2 omega u, t epsilon chi c epsilon grad u epsilon, which is sort of restriction of unfolding operator on c epsilon that we have denoted by t epsilon c. So t epsilon c grad u epsilon weakly converges to chi c y1 x2 neta 1 neta 2 in L2 omega cu square, and t epsilon chi I epsilon grad u epsilon weakly converges to chi I y1 x2 z x comma y1, and as z is a vector, so this is chi I y1 x2 z1 z2 in L2 omega u square. So this convergence happen in weak cells, and these are up to subsequence. So finally we have to prove this full convergence subsequence also. So now we have to identify what is our eta 1, eta 2, z1, z2, and what is how they are related with u naught. So yeah, first we'll find u naught, because we have a h1 bound on C epsilon, that is in conductive part. We're going to have this u naught going to have this representation, that is u naught x is equal to u plus u1 x comma y1, where u1 is supported only on the unfolded domain corresponding to insulating part. That is u1 will be 0 on omega cu. So there are sort of analysis involved. I'm just sketching the proof. That's it. So here basically we have used these two properties. That is T epsilon cu weakly converges to u naught x y1 omega cu, and it will be independent of y1 on this region because of this equality. That is del y1 T epsilon c u epsilon plus is equal to epsilon T epsilon c del u epsilon del x1. So this, and we put like pass epsilon tends to 0, we see this going to be 0. So because of this relation, we're going to have this kind of decomposition of u naught. Also, we're going to have del u plus del x2 belongs to L2 omega plus, and meta 2 basically will be your del u plus del x2, and z2 x comma y going to be 0 in omega iu. So basically, we have find out what is eta 2 z2 we have found. So now only thing left is what is your eta 1 and what is z1. So let us find out what is eta 1. In order to find eta 1, we will use oscillating test function. So just take psi epsilon x is equal to epsilon psi x comma x1 by epsilon as a test function in 1, where psi belongs to cc infinity omega plus and ct infinity omega plus colon c infinity par 0 1, and psi is 0 on omega iu, that is unfolded domain corresponding to insulating part. And use this test function at epsilon level, apply unfolding operator, use whatever the convergence we have till now. If you pass to the limit epsilon tends to 0, we'll end up with this equality 3. So this is true for all psi. So that basically tells you eta 1 is equal to 0 on omega cu. That is conductive part, it is 0. Now we have to find what is z1. So z1 is basically going to be your del u1 del y1. So to see this, we're going to use a test function like this. So here psi epsilon x is psi x comma x1 by epsilon. Psi belongs to cc infinity omega u with one periodic in y1, but here psi is 0 1 omega cu. Now consider this equality, series of equality. So in the left part, if you apply unfolding, we're going to have this right part. Now here we can, if you interchange the unfolding operator and the derivative with respect to x1, we're going to have 1 by epsilon extra. That 1 by epsilon extra will cut this epsilon. Now we have convergence, this t epsilon e epsilon plus and del w, and we have this convergence, and this is a nice function. So we're going to have convergence like this will convergence to del psi del y1. So if so now we can pass to the limit in the right hand side, and if we apply unfolding operator on the left hand side, and we have already assumed that t epsilon chi epsilon del epsilon del x1 converges to z1. So if we pass to the limit on both sides, we're going to have this equality. Here this equality in the right hand side, if we just do integration by parts, we're going to have z1 is nothing but your del u1 del y1. So we have also identified what is our z1. Now the u plus should belong to the limit function space h omega. In order to have u in h omega, this you should agree u, that is u plus and u minus, they should agree on the interface. For that, what you do, we just take a function belongs to cc infinity omega u, and phi is equal to 0 on all the boundary of omega cu except the bottom boundary, that is gamma cu, and just apply simple integration by parts. Now on the interface at epsilon stage, u epsilon plus is same as e epsilon minus. So if you just replace e epsilon plus by epsilon minus in this boundary term, that is integral over omega cu, and pass to the limit epsilon tends to 0, we'll end up with this integral equality. And this is true for all phi belongs to c infinity omega cu bar with phi is equal to 0 on all the boundary except this bottom boundary. So basically this tells you phi u plus is equal to u minus on gamma cu. But since u plus and u minus both are independent of y1, that tells you u plus is equal to u minus on interface. So basically that u plus that is u plus and u minus belongs to h omega. Now, if we take a test function phi epsilon as phi x plus phi 1 x comma epsilon, use this test function in this epsilon stage variational form, where phi 1 is 1 periodic in y1 and 0 in omega cu. And if you pass to the limit epsilon tends to 0, we'll end up with this two-scale variational form, that is limit variational form. So we can see that we have sort of decomposed between the conductive region and the insulating region, that is omega iu and omega cu. So this dependence with respect to y1 mostly captured in this part, that is omega iu. So now for this limit here itself, we can prove the existence and like uniqueness of u plus, u minus, and u1. Okay, now we try to decompose this variational form. So first, if you put phi is equal to 0 in the above equality, we're going to end up with this equality, that is integral of omega plus yx2 del u1 del y1 del phi1 del y1 plus integral of omega plus yx2 u1 phi1 plus integral of omega plus yx2 f minus u plus phi. You see that this is a different sort of partial differential equation with respect to y1. Okay, so here and f minus u plus is independent of y1. So using the cell problem that you have defined in the beginning, we can write our u1 as u1 x comma y1 is equal to fx minus u plus x xi x2 y1. Now, if you put phi 1 is equal to 0 in the limit to scale variational form, and if you replace the definition of u1 in the variational form, we'll end up with this equality, this variational equality. It is in place of u1, we have replaced this f minus u plus xi, and we just integrate with respect to y1. So we have this one. So yx2 minus integral of yix2 xi du1. If you recall, this alpha x, alpha x is we have denoted by this quantity. Now we have this variational form, and this is true for while phi belongs to c infinity omega bar. Okay, so basically, so this should be hold for while phi belongs to h omega. Now to show that this to show the full convergence of the sequence, basically we have shown that u plus, u minus, all these limits are up to subsequence. Now to have the convergence of the full sequence, we need to show that this limit variational form, this limit problem has a unique solution. So in order to do that, we need to show that quantity alpha x, that is this one, yx2 minus integral over yix2 xi dy1 is strictly positive, because the first of all ycx2 is already positive. So for that part we don't care. But for the second term, that is yx2 minus integral over yx2 xi dy1, we have to show that it is positive. So for that, what we'll do, we just take w is equal to xi in the test function in the cell problem. We'll end up with this equality. So we have del xi del y1 square plus xi square is equal to integral yx2 xi. So just recall that xi is supported on yix2, that is projection corresponding to the insulating part. So that gives you norm xi L2 yix2 is less than equals to measure of yix2 to the half. So just in the right hand side, apply just Holder's inequality. That's it. Then we have just consider this alpha x, that is yx2 minus integral over yix2 xi. So this is greater or equal to measure of yx2 minus apply Holder's inequality in this part, that is yix2 into yix2 xi. We have minus yix2 to the half norm xi L2 yix2. So this is nothing but yx2 minus, because this norm xi L2 yx2 is less than yix2 to the half. So that gives you yx2 minus yix2, and which is nothing but ycx2, that is conductive part, and which is strictly greater than delta from our assumptions. So that tells you that this alpha x is strictly positive, right? So basically this tells you this variational problem has a unique solution. So we have all the convergence, and we have u plus and u minus is a unique solution. So that proves our convergence of the whole theorem. Okay. Yeah. So now we'll try to see the what will happen if we put control on the conductive region. So for theta epsilon belongs to L2 C epsilon, just consider the L2 cost functional, that is G epsilon U epsilon theta epsilon is equal to 1 by 2 integral omega epsilon U epsilon minus UD square plus beta by 2 integral over C epsilon norm theta epsilon square, where UD is the desired state and U epsilon satisfy the similar sort that same variational form, but with extra term in the right hand side, that is our interior control. So we have a state equation exactly in same structure, but in the right hand side we add this term. So basically we are applying control on C epsilon. That's why we just multiply a chi epsilon factor, chi C epsilon factor before theta epsilon. The existence of state term is again given by the Lax-Milgram lemma. Okay. Now the optimal control problem is to find a U epsilon bar, theta epsilon bar belongs to H1 omega epsilon cross L2 C epsilon, such that J epsilon evaluated at U epsilon bar, theta epsilon bar going to be the infimum of J epsilon, U epsilon, theta epsilon, where U epsilon, theta epsilon pair satisfy the above state equation. Now, classical result from calculus of variation gives you the existence of such E epsilon bar and theta epsilon bar. So here our aim is to analyze the asymptotic behavior of E epsilon bar and theta epsilon bar. So in order to analyze the asymptotic behavior of this optimal state, that is E epsilon bar, and optimal control theta epsilon bar, we'll use the characterization of this optimal control. For that, what you'll do, in order to do that, we need to introduce adjoint variational form corresponding to the state equation. That is given by find V epsilon bar H1 omega epsilon such that it satisfies this variational form. So that is, so the structure of the variational form, the adjoint variational form is same, except in the right hand side we're going to have E epsilon bar minus UD times phi for all phi belongs to G, for all phi belongs to H1 omega epsilon. Again, by Lax-Milgram lemma, we have existence of V epsilon bar. Okay. Now, what is the characterization theorem tells us that suppose E epsilon bar and theta epsilon bar be the optimal solution to the considered optimal control problem, and V epsilon bar be the unique solution of phi, then the optimal control theta epsilon bar characterized by theta epsilon bar minus chi C epsilon 1 by beta V epsilon bar. Now, if you see the characterization of theta epsilon bar, basically it is restriction of V epsilon bar on conductive part, and on conductive part V epsilon bar has H1 uniform bound, and that makes for conductive region our analysis little bit easier. Okay, because you have H1 bounds, we can have all sort of convergence of theta epsilon bar. So just to see the limit control problem, what will be the limit optimal control problem? So the limit optimal control problem for this case, it is given by find theta belongs to L2 omega plus such that limit cost functional J U comma U1 comma theta is given by 1 by 2 integral over omega U plus U1 minus UD square plus 1 by 2 omega minus U bar, so U minus UD square plus beta by 2 integral over omega Cu no mod theta square, where U and U1 satisfy this following to this two-scale system, that is find U comma U1 belongs to H omega times V omega such that integral omega Cu. So if you see the left part is exactly the limit variational form we get in the beginning, but in the right hand side we're going to have F plus chi C y1 x2 theta times phi plus phi1 plus integral or omega minus F phi. So this extra term that comes from the control, but the thing is that this theta is independent of y1. That makes this separation of scale, all these things little bit easier. So just to see the characterization of the limit control, we need to, okay, so yeah, and the optimal control problem is find U bar U1 bar theta bar belongs to H omega V omega L2 omega plus such that J evaluated at U bar U1 bar theta bar gives you the infimum of all such J U U1 theta, where U U1 theta pair satisfy the state this above state equation. In order to characterize the limit optimal control, we just use this this two-scale adjoint variational form. So again, the right hand side structure is same, that is find V bar V1 bar belongs to H omega cross V omega such that this variational inequality is satisfied. Again, left hand side is same as it is in the variational form, but in the right hand side we're going to have U bar plus U1 bar minus UD times phi plus phi1 plus integral over omega minus U bar minus UD times phi for all phi comma phi1 belongs to H omega cross V omega. So using this, so basically this V bar and V1 is a limit of T epsilon V epsilon. So that like we can prove as earlier. Okay. So using this adjoint state, we can characterize our optimal control as, so we have like u bar, u1 bar, theta bar is the optimal state, v bar, v1 is the adjoint state. Then the optimal control theta bar is given by minus 1 by beta v bar x. You see this theta bar is not affect, I mean this theta bar is not sort of affected by u1 bar. So basically it is fully independent of y1. So because of this, we can easily separate the scale for this case. So in this case, using the cell problem, we can write the separated cost functional as j u comma theta as 1 by 2 omega plus integral over yx to 1 minus xi u plus f xi minus ud square plus 1 by 2 omega minus u minus ud square plus beta by 2 omega plus, and because theta is independent of y1, so it's given by yc x2 mod theta square. And the scale separated limit state equation is given by find u belongs to h omega such that this left hand side the same structure as the variational form. In the beginning we have homogenized, but the right hand side we are going to have extra alpha x fp plus integral omega minus fp plus integral omega plus yc x to theta phi, where theta basically is our theta is our control for all 5 units to h omega. But all sort of like contribution from insulating part, all these things are reflected in the adjoint state. So the scale separated adjoint state is given by, again the left part is the structure same like as the state equation, but the right hand side like several contribution coming from the insulating part and scale like cell problem. So you see that, so in the right hand side we have integral omega plus integral over yx2 1 minus xi squared dy1 u bar plus alpha x as in the beginning we have defined minus alpha x ud plus integral over y ix2 xi minus xi squared dy1 if into phi plus integral over omega minus u bar minus ud into phi. So this is the scale separated adjoint equation. So if you know the adjoint state, cost functional and state equation, that means you know your full optimal control problem. So we have, for this case, we are able to separate the scale from the two scale form. Now we'll see what we, and that happens because we have a uniform bound on the control, h1 uniform bound on the control. But if we apply the control on I epsilon, that is we have the same cost functional, that is L2 cost function, but we are applying control on I epsilon, that is beta by 2 integral y I epsilon theta epsilon square, where theta epsilon belongs to L2 I epsilon, and E epsilon satisfies the same variational form, except here we are applying the control on the insulating part, that is integral over omega epsilon chi I epsilon theta epsilon phi. So this extra term here coming because of we are applying control on the insulating part. Again, the existence of state equation for this case is given by Laxmi-Graham lemma. And in this case, the optimal control is find u epsilon bar theta epsilon bar belongs to h1 omega epsilon plus L2 I epsilon such that j epsilon evaluated at e epsilon bar theta epsilon bar is the infimum of j epsilon e epsilon theta epsilon for all e epsilon theta epsilon satisfy this state equation, that is A. So for this case, if you see the characterization for this control problem, we have this characterization, that is if you have e epsilon bar theta epsilon bar as optimal solution, then your optimal control theta epsilon bar is characterized by theta epsilon bar is equal to minus chi I epsilon 1 by beta v epsilon bar. Now this v epsilon bar, basically theta epsilon bar is depend on v epsilon for x belongs to I epsilon. So basically theta epsilon bar doesn't have h1 bound because v epsilon bar doesn't have h1 uniform bound, because on I epsilon like h1 norm of v epsilon is sort of order of 1 by epsilon, and that gives the more trouble here. So we try to for this problem we will not be able to get fully scale separated form, but we will try to separate as much as we can. So for this problem, if you see the limit optimal control problem, the limit optimal control, the control going to have on two parts, because if you remember, like we have on I epsilon, we're going to have like E epsilon converges to U plus and U1. So similarly, for this problem, theta epsilon restricted to an insulating part will converges to theta plus and theta 1. So you have like two component type things. So for this control on I epsilon, the limit cost functional will become like this. So first two term is same, but the last term will be beta by 2, 1 by 2 omega iu theta plus theta 1 square, where u plus u1 satisfy this two scale variational form. Again, left part the structure same as it is, but with f you have chi I y1 x2 theta plus theta 1 phi plus phi1 plus integral omega minus f phi. So this chi, earlier it was dependent on chi c, and we have only one control, that is theta, and theta is independent of y1. But here we have like theta and theta 1. Theta part is independent of x, that is fine, but we have theta 1 which is sort of depend on y1, and because of this will not be able to separate fully the scale, that is macro scale. So in the limit also we're going to have some sort of contribution, like some coupled with the micro scale. So for this case, the limit optimal control problem is find u bar u1 bar theta 1 bar belongs to h omega v omega cross L2 omega cross L2 omega iu, such that j evaluated at u bar u1 bar theta 1 bar is the infimum of j of u1 theta 1, where u1 theta 1 satisfy the above state equation. Now, if we again by try to separate the scale, for this case we will not be able to separate fully, but we sort of partially separate the scale. So for this case, the reduced cost functional will be the first two term will be as it is, sort of not as it is, but we have one extra u11 term. So that's u11 is not fully separated. U11 has dependency on y1. So we have 1 minus xi u plus xi f plus u11 minus ud, and lower part it will not going to be changed, like it will be as it is, because there is no effect of insulation or anything. But the cost functional will be integral of yx2 theta plus theta y1 square, because you have theta 1, because theta 1 is dependent on y1. That's why we cannot write this like earlier we have integral omega plus measure of yx2, but here we don't have because of theta 1. Again, the cost functional going to have couple system. Sorry, the state equation is going to be a couple system. As earlier we have like one full variational equality, but here is going to have couple system. So what we have? So the state equation is find u bar and u11 bar belongs to h omega cross v omega, which satisfy this following equality. So the first variational form, left part has same structure, but with right hand side we have 1 minus xi f plus 1 minus xi theta plus theta 1 into phi plus integral omega minus f phi minus, which is coupled with a micro state, that is integral omega u del u11 del y1 del phi del y1 plus integral over omega u11 phi is equal to integral over omega u theta plus theta 1 phi. So you have like couple system for the state equation. So similar sort of adjoint equation will be the same sort of structure. So the adjoint state will be like, for the first part, left hand side same structure, but right hand side have, in the lower part it is same, but in the upper part we have integral omega plus yx2 1 minus xi square u bar plus xi 1 minus xi f into phi plus integral over omega plus yx2 1 minus xi u11 bar minus 1 minus xi ud into phi plus, and the adjoint micro adjoint state is given by del v, so integral over omega u del v bar del v11 v bar into del y1 plus del phi1 del y1 plus integral over omega u v11 bar into phi plus this 1 minus xi u bar plus xi f plus u11 bar minus ud into phi1, for all phi comma phi1 belongs to h omega into v omega. So using this adjoint state, we can characterize our sort of reduced optimal control problem as this. That is, the optimal control is now given by theta bar plus theta 1 is equal to minus 1 by beta 1 minus I V bar plus V11 bar in omega IU. Now we have a partial separation of this optimal control. That is, theta bar is minus 1 by beta V bar plus, and theta 1 bar is given by minus 1 by beta xi V bar plus V11 bar. So we have this much scale separation, but till now we are not able to done more scale separation on this. We have this much reduced form of this optimal control problem when we apply control on IF cell. Okay. So the thing is that in this problem we have sort of took the coefficient as 1 on epsilon square. So this whatever we have done can be carried out. We can take like coefficient on the conductive region is order of 1, and the coefficient with insulating region of alpha epsilon, where alpha epsilon tends to 0, and there will be like 3 regime, like according to the limit k, where k is equal to limit epsilon tends to 0, alpha epsilon by epsilon. And according to that, we're going to have 3 different problems, like if k is equal to 0, k is equal to infinity, and k lies between 0 to infinity. So here, whatever we have done is for k lies between 0 to infinity, that is k is equal to 1. Basically, in our case, alpha epsilon is equal to epsilon. So limit epsilon tends to 0, epsilon by epsilon, that is 1. Okay, so we can carry it out this whole whatever we have done in this setup also. Okay, but if you do in this setup, so for this case, like for k lies between 0 to 1, so if here we have k is equal to 1, if you take arbitrary k, that is like for any k belongs to 0 to infinity, the only changes will be in the cell problem. In the cell problem, we have the coefficient, the first term, that is del square xi del y1 square. So the coefficient instead of 1, there will be k square. That's it. There won't be any more changes here. And for the other 2 cases, it can be done by just some minor changes, k is equal to 0 and k is equal to infinity. So the case lies between 0 to infinity is a critical case that we have studied. So there are some references. That is the first, basically this is a generalization of the work by Guardiola and Alicelli. And this work to see the problem on this multi-scale analysis on this kind of domain, when you can look at the averaging process in periodic media by Bakalov and Panasenko. And then another work is given by Kosharev. And this work recently appeared in Journal of Differential Equation. Yeah. Thank you.
Thank you, Abu. ¿Alguien tiene pregunta, duda, comentario, algo?
I have a question.
Sí, please, go ahead.
So when you deal with high contrast
Yes.
medium, sometimes some kind of non-local problem is observed. So here I don't see any such thing. So
Yeah.
is
The
there...
non-local problem is the cell problem, basically, right? This is integral. We see that cell problem is sort of the non-local one that is given by, yeah, this one, right? So non-local in the sense you are saying that
no, this is local.
This is maybe because of we are dealing with linear equation, that's why this doesn't appear.
I'm not so sure. I mean, maybe it's more like a commentary. I mean, so it might be worthwhile for you to look at the literature. Think Alicelli and Bushite, they have works, Berlioz, which you named in fact in your this thing.
Yes.
They have interesting results. So maybe there are unexplored maybe cases, situations.
What that
I agree with Raja.
Yeah, because we have like very restrictive oscillating domain, that's why maybe we have basically here we are able to separate the scale in by using the cross-sectional cell problem. We are able to separate the scale. That's why if you are able to separate the scale, then there is no chance of appearing no local problem, right? Because here we are fully separate for this problem. Maybe in the
maybe.
last, when you apply the control on IF7, there have some couple systems. So there may be sort of something is hidden as non-local problem. But that last part we are not able to separate. This one, like for example, this problem, right? So U11 will not able to separate, and U1 involved here, right? So so there maybe the non-localness is involved. I'm not because we didn't able to separate fully this part.
Okay. Yeah.
It's not only you. It's there are lots of paper where they are not. It means even the paper by Anna Kumaran and Alisili, they were not able to separate.
Yes, yes.
So one commentary very quickly from the application point of view, that you applied the control inside the domain, that is practically not possible. Practically possible case is that you apply the control on the flat top part, and there are lots of scope because you have two different types of metal. There is a separation, right? So you can apply two different type of control on the top flat part, and it will create miracle in the limit problem. One more thing that is very important to observe here. I don't know, maybe at the time you will get the experience. And first of all, if you want to apply the control on the flat part, you need to come out of the homogeneous Dirichlet setup. If you see the paper of mine with Rajesh and Nandakumar, there we consider the non-linear boundary data. Okay.
Yes, yes, yeah, that we will.
And there, if you put the control, then this will be really a different type of limit problem you will get.
Okay.
Okay, and if you talk, if in your setup where you don't have any control on the flat part, on the boundary, if you go for the inner distributed control, then you can consider the top part to be pointed. It's not needed to consider the flat portion on the top. It is the recent work we did with Ayyappan.
Yes, that
which is about to be published. Yes.
Yes. Yeah, this work basically done earlier. Now I've just told me recently.
Yes, true, correct. Yeah, so maybe for your information, Rajesh, after that conference, observed that we should try that, and I told him that this thing people were working on this. And one thing which you have to do, that the domain you are saying in the beginning, that any general domain can be considered, and you are taking it for the simplicity. That's not true.
No.
If you take any general domain, your limit problem will be completely different than the limit problem what you are getting. If you want to see this, see the book by Melnick. He has a book.
No. Yes, that I have. Basically, any sort of general means like it is connected, right? One-dimensional living measure, all these things.
No. Your domain is actually defined by a function. It is possible that you don't.
No.
For example, the fourth domain. The fourth domain is not even the function. The fourth domain in your figure, figure which you are showing, the fourth domain is not possible defined by a function. It is just defined by a relationship.
This one, right?
Yeah.
That's sort. Basically, this one. So this sort of things is easily like we can analyze whole thing by this sort of domain also, because recently that Damlamian book also, right? They have
Melnick book.
Melnick book, I don't know. The Damlamian has the unfolding operator book. He just published.
That recent book. Yes.
Recent book, recent book. They have like we in Ayyappan paper we have given yx2 by a function, eta function, right?
Correct.
But that is not necessarily given by eta function. It can be the cross section and just take projection.
Correct.
So as long as this cross section is connected there, because recently that Melnick shows if you have cross section is disconnected, then they are going to be like sort of multi-seeded function space thing.
Correct.
So that's why
and then you will have more information about the limit problem. That's what I'm saying, that you whatever you are saying that the problem, your simplification, that's not true. The limit problem is completely different if you go for more general domains.
More general in the sense like it is not given by function. General means the domain cannot be given by function. That's what I generally mean here.
Correct. Okay. No, but your work is very nice. I like that. Congratulations for that. It's a very nice job.
Yeah, thank you.
Anybody, ¿alguien más quiere comentar algo? Rápidamente, porque ya se acabaron horas. ¿No? Entonces terminamos la reunión. Nos vemos próximo jueves a las 3.
See you. Nice
Okay.
talk.